Now, if you look at page 2 of your topical worksheet, this is actually June 2022 P41. At the first question, state Wien's displacement law. Wien's displacement law states that the wavelength of maximum intensity is inversely proportional to the thermodynamic temperature. If you write it out in the form of an equation, it's actually lambda max being inversely proportional to your thermodynamic temperature. This is what Wien's displacement law is. Then moving on to the next part of your question, figure 10.1 shows the wavelength distributions of electromagnetic radiation emitted by two stars A and B. The surface temperature of star A is known to be 5800 Kelvin. So when you see a graph shape that looks like this, you are probably going to be using Wien's displacement law in the following question. So let's just look at the wavelength at maximum intensity first. For star A, which is this curve in orange right now, we already know that the surface temperature is 5800 Kelvin. This is what the question already stated. So from here, we are interested to know what is the wavelength at maximum intensity or the wavelength at peak intensity. So it should be this point here. If you read out the wavelength, you will see that the value is actually 0.5. So the wavelength at maximum intensity for star A is 0.5 micrometer. And then after that, when you're talking about star B, which is this green colored curve here, the wavelength at peak intensity is going to be right over here. We are interested in the wavelength value. That one should give us roughly 0.65 if you read it very carefully. So the wavelength for star B is going to be 0.65 micrometer. These are the wavelengths at peak intensity. Okay. Then moving on to the actual question itself, you're supposed to determine the surface temperature of star B. This is where Wien's displacement law that you just defined comes into play, where you stated that the wavelength at maximum intensity is inversely proportional to the thermodynamic temperature. You want to find out the surface temperature of star B. So you can work out some sort of ratio relationship here, where lambda B over lambda A is equals to TA over TB. Bearing in mind that this value of wavelengths here is the wavelength at maximum intensity. Okay, so sometimes when you use Wien's displacement law, you always say it's lambda max here. It is very easy to misunderstand it as the maximum possible wavelength value. That's not the case here. It really refers to the wavelength that you have at maximum intensity, okay, which is not necessarily the largest possible wavelength value, okay? So you already found out the wavelength at maximum intensity for star A and star B right over here. So what you're going to do is that you're just going to substitute in the value. The wavelength at maximum intensity for star B is 0.65, whereas that for star A is 0.5. The units are in micrometer, but you don't really need to change it from micrometer to meter because you can see that the units will cancel each other off. If this one is micrometer and this one is micrometer, they will eventually cancel off. So you can just leave the unit as it is. And then the surface temperature of star A is already stated by the question to be 5800 Kelvin. So from here, you can now find out what is surface temperature of star B. The answer is going to be 4.46 times 10 power 3 Kelvin. Okay. For part 2, star B appears less bright than star A when viewed from the Earth. Use figure 10.1 to suggest with a reason how else the physical appearance of star B compares to that of star A. So if you try to recall the shape of the wavelength distribution graph for star A and star B, it was a graph of intensity versus wavelength. Star A looked something like this, where the wavelength at peak intensity was at 0.5. This one is the wavelength at peak intensity for star A. And then for star B, you had a graph that looked somewhat like this, And then when it came to the wavelength at peak intensity for star B, it was somewhere around here at 0.65. This is the wavelength at peak intensity for star B. So you're supposed to make use of this graph shape here to describe how else would the physical appearance of star B be when compared to star A. So right now, if you look at the wavelength at peak intensity for both stars, star A is right over here, whereas star B is right over here. So you can see that the wavelength at peak intensity for star B is actually larger than that of star A. You could say that star B has greater peak wavelength or average wavelength. This in turn would cause your star B to look redder. You need to relate this to your visible light spectrum, Roy G. Beef. If you're going towards the right side, this is where wavelength was decreasing. But if you're going the opposite side towards the left, this is where your wavelength is increasing. So because your star B is having a larger wavelength than star A, you could say that the wavelength is increasing. So when the wavelength is increasing, it's actually going towards the red end of your visible spectrum. It will actually appear to be redder. That's why here you can say that star B looks redder. All right. Now, moving on to the last part of your question in part C, the lines in figure 10.1 have been corrected for redshift. State what is meant by redshift. Redshift is where the apparent wavelength observed is greater, or you could also say that the wavelength is greater than the known value that you get from the laboratory due to movement of star away from the observer. So for your first point, either you say apparent wavelength is greater or wavelength is greater than the known value. And then for your second point, you say this is due to the movement of star away from your observer. This is what redshift actually is. In part 2, explain how cosmologists are able to determine that light from a distant star has undergone redshift. You do this by examining the lines in the spectrum of light from the star being studied, which can be in the form of an absorption spectrum or an emission spectrum, and then subsequently comparing it with a known spectrum. If you notice that there's an apparent increase in your wavelength, then you have undergone redshift. All right. Now, if you look at page 6 of your worksheet, this will be November 2022 P42. For this part of your question, figure 9.1 shows the visible part of the emission spectrum from hydrogen gas in the laboratory on the Earth. The numbers indicate the wavelength in nanometer represented by each line. So what you have here is the emission spectrum done in a laboratory. You can think of this as your reference emission spectrum. And then moving on to part B, the same part of the emission spectrum from hydrogen as in A is observed in light from stars in a distant galaxy as shown in figure 9.3 below. Again, the numbers indicate the wavelengths in nanometer. So this is the emission spectrum from a distant star. The spectrum shows the same pattern as figure 9.1 but with different wavelengths. In part 1, state the name of the phenomenon that gives rise to the change in the wavelengths. So if you look at the reference emission spectrum and the emission spectrum from the distant star, look at the lines one by one. The first line is 411 nanometer, then it became 429 nanometer, and then the next one is 435 nanometer, it eventually became 454 nanometer, and then you have 418 nanometer here, it became 509 nanometer, and then for the last one, you have 615 nanometer, it becomes 686 nanometer. So overall, you can see that there's actually an increase in wavelength. So since there's an increase in wavelength, there's an increase in apparent wavelength, you know this is actually redshift. For the next part, state what this phenomenon shows about the motion of the galaxy. You know that your observed wavelength has increased. This in turn means your observed frequency has decreased. If you relate this to Doppler effect, you could say that your source is moving away from your observer. So your answer here is moving away from the observer. For the next part, use one of the lines in figure 9.1 and the corresponding line in figure 9.3 to determine the speed of the distant galaxy relative to the observer. The question has already stated to you to use one of the lines only, and they want the speed of the distant galaxy relative to the observer. They want the speed with which the galaxy is moving away from the observer. Since we are talking about the redshift here, there is a certain equation that is always used when it comes to calculating redshift. That one being that the fractional change in your wavelength is equals to the fractional change in your frequency equals to the recessional speed divided by the speed of light. So you want the recessional speed right now, the speed with which the galaxy is moving away from your observer. And since information about the wavelength is given here, you're going to use the fractional change in wavelength and equate it to your recessional speed divided by your speed of light. So right now, your equation is delta lambda over lambda equals to V over C. Since the question asks you to just use one of the lines, I'm going to use 658 nanometer increase to 686 nanometer, so that the change in your wavelength is 686 minus 658 divided by the original wavelength value of 658, and then equate it to your recessional speed divided by speed of light, 3 times 10 power 8. Eventually, you'll be able to find the answer as 1.28 times 10 power 7 meter per second. Now, you can actually likewise repeat your calculation for different lines, say 411 and 429, 435 and 454, and also 488 and 509. Okay, just use either one of the lines, all right? So for the last part, the galaxy in B is known to be a distance of 5.7 times 10 power 24 meter from the Earth. Use your answer in B3 to determine a value for the Hubble constant h0. So the answer in B3 is actually your recessional velocity, and you are given information about your distance here so that you can find out your Hubble constant. You would have to make use of Hubble's law, which gave you the equation V is equals to h naught d. So you already know the recessional velocity in your previous question, 1.28 times 10 power 7. You now know your distance of 5.7 times 10 power 24. You can subsequently work out what is your Hubble constant. It's going to be 2.25 times 10 power minus 18 per second. All right. Now for the last question in page 4 of your worksheet, you have June 2022 P42. For the first question, state Hubble's law. Hubble's law states that the speed of recession of your galaxy from observer is directly proportional to the distance of the galaxy away from the observer. You could say that V is directly proportional to D, and then when you want to get rid of the proportionality sign, you introduce a constant, which is your Hubble constant, such that now V is equals to H naught D. This is what you know as Hubble's equation. For part 2, explain how cosmologists use observations of emission spectra from stars in distant galaxies to determine that the universe is expanding. Wavelength or spectral lines observed are greater than their known values. The wavelength is observed to have increased. The apparent wavelength increases. This means that you have redshift. Redshift shows that stars in distant galaxies are moving away from the Earth. Therefore, the universe is expanding. If you recall what redshift was actually talking about, it said that your wavelength observed increases. So your observed frequency was decreasing. If you relate it to Doppler's effect, that meant that source is moving away from your observer. That's why you could say that because you saw redshift, that means source is moving away from your observer. Your stars are going away from the Earth. The universe is therefore expanding. Okay. Now, for the last question, explain how Hubble's law and the idea of the expanding universe lead to the Big Bang theory of the origin of the universe. This is a 3-mark question. So for the first point, you can say that all parts of the universe are moving away from each other. You concluded this from observing redshift. And then for the second point, you can say that more distant objects are moving away faster. You concluded this from Hubble's law. By considering these 2 points, you can then say that matter must have been close together or very dense in the past. Let's consider this. If right now everything is moving away from each other, if you can stop the time and rewind it, that would have meant that everything else was actually closer in the past. If you take this idea further and rewind time to the beginning of time itself, this would have meant that everything began from a single point. Hence, you can say that they were all very close together or very dense in the past. And then from there, they started expanding with time, and they're still expanding even now. This is what we mean by the Big Bang Theory to explain the origin of the universe. Okay, so this is the last question.